Welcome back to Computer Lessons.
If you used computers in the early 1990s, you remember the nightmare of connecting a simple device. You had a massive parallel port for your printer, a serial port for your modem, a PS2 port for your mouse, and a game port for your joystick. None of them were compatible with each other, and you often had to restart the entire computer just to get them to work. It was a chaotic landscape of proprietary engineering where every device spoke a different language. Connecting a scanner was not a simple task. It was an afternoon project involving screws, dip switches, and frustration. But in the late 90s, a team of engineers led by Ajay Bhatt at Intel had a radical idea. They envisioned a single universal connector that could handle data, power, and audio all at once. They wanted a system where you could plug a device in while the computer was running, and it would just work. This dream became the Universal Serial Bus, or USB, a technology that would go on to conquer the entire planet. Let's look at the anatomy of the classic USB Type-A connector, the rectangular one we all know. Inside that metal shield, there are just 4 simple pins. On the outside edges, you have the power pin, 5 volts, and the ground pin. In the middle, you have 2 data pins, data plus and data minus. This design is intentional and brilliant engineering. The power pins are physically longer than the data pins. This means that when you plug a USB stick in, the power connects first to wake up the chip, and the data connects milliseconds later. This prevents electrical surges that could fry the data controller. It allows for hot swapping, the ability to plug and unplug devices without shutting down the PC. The serial in Universal Serial Bus refers to how the data moves. Old printer ports were parallel, meaning they sent 8 bits at a time across 8 separate wires. While theoretically faster, the wires interfered with each other, limiting the cable length and speed. USB sends data serially, 1 bit at a time, very remarkably fast. USB 1.1 could move 12 megabits per second, which was enough for keyboards and mice. But as we moved into the era of digital cameras and MP3 players, we needed more speed. In the year 2000, USB 2.0 arrived, boosting speeds to 480 megabits per second. This was the high-speed era that made the iPod and flash drives viable. However, USB 2.0 was a half-duplex system, meaning data could only travel in one direction at a time like a walkie-talkie. Then came the Blue Revolution, USB 3.0. If you look inside a blue USB port, you will see the original 4 pins for backward compatibility, but deep inside there are 5 extra pins. These extra lanes allow for full duplex communication, sending and receiving data simultaneously at 5 gigabits per second. While the Type-A connector stayed the same on the computer side, the device side was a mess of different shapes. We had the square Type-B for printers. We had mini USB for early cameras, and micro USB for Android phones. Micro USB was a mechanical failure. It had tiny hooks that wore out, causing cables to become loose and fail to charge. And let's not forget the USB superposition problem of Type-A. You try to plug it in, it doesn't fit. You flip it over, it still doesn't fit. You flip it back to the original side and suddenly it fits. This design flaw existed because making the connector reversible in the 90s would have doubled the cost, and they needed it to be cheap to succeed. Finally, in 2014, the prophecy was fulfilled with USB-C. This is a masterpiece of connector engineering. It is completely reversible with 24 pins packed into a tiny oval. USB-C is not just a data cable, it is a shapeshifter. Through alternate modes, it can transform into a display port to drive a 4K monitor or an HDMI port for your TV. It essentially acts as a physical tunnel that can carry almost any other signal protocol inside it. The most game-changing feature of Type-C is power delivery, or PD. Old USB ports provided just 2.5 watts, barely enough to charge a phone slowly. Modern USB-C PD can negotiate up to 240 watts of power. This means the same cable that charges your earbuds can also power a high-performance gaming laptop. The charger and the device talk to each other, shaking hands digitally to agree on the exact voltage and amperage needed. It is a smart power grid in a cable. However, this universality created a new problem: confusion. Not all USB-C cables are created equal. Some cheap cables connect physically but only run at slow USB 2.0 speeds, while others support high-speed Thunderbolt 4. Thunderbolt is a technology developed by Intel and Apple that uses the USB-C shape but connects directly to the PCIe lanes of your motherboard. It is blazingly fast, reaching 40 or 80 gigabits per second. It is effectively an external version of the internal slots we discussed in the motherboard video. With USB 4, these standards are finally converging. USB 4 basically incorporates Thunderbolt technology, aiming to make every high-end cable capable of doing everything. But with great power comes great security risk. Because USB has direct access to the hardware, it is a vector for attacks. Juice jacking happens when you plug your phone into a public charging station at an airport. The station might be rigged to steal data from your phone while it charges. This is why you should always use a data blocker or a simple power-only cable when charging in public. There is also the malicious USB killer. This looks like a flash drive but contains high-voltage capacitors. When plugged in, it charges the capacitors from the USB power and then discharges 200 volts back into the data lines. This instantly fries the motherboard of almost any computer. Never plug a random USB drive you found on the street into your machine. Despite these risks, USB is a triumph of standardization. Ajay Bhatt and his team didn't make a cent from the patent. They made it an open standard to improve the world of computing. Today, billions of devices connect seamlessly because of that decision. We have moved from the mechanical chaos of the 90s to a sleek, unified digital ecosystem. We have covered the hardware inside the box and the peripherals outside the box. But a computer is not an island. To unlock its true potential, it needs to connect to other computers. It needs to join the hive mind. In the next video, we are going to start our massive series on the internet. We will explain the physical infrastructure of the web, from the massive undersea cables to the data centers that hold our digital lives. We are leaving the desktop and entering the network.
Tell me in the comments, how many times do you usually have to flip a USB-A cable before it finally fits? Be honest, is it always 3? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.